The power of lens. The power of refraction is a measure of power of lens. Lens, as you know, is a combination of two surfaces, maybe spherical or plane surfaces. In lens, we have two types of lenses, the converging lens and the diverging lens. Converging means the incident rays, all the incident rays after passing through the lens getting refracted and converge to a point on the principal axis. Always come together to a point. It is called as convergence, where the image is forming. And this point is called as focal point of the lens, where we get the image. And the distance between this point and the optical center is called as focal length of the lens, f. This is always lies towards the right side, and f will take positive value, because as a sign convention, it is on the right side. We are measuring the length from this point to this point in this direction. It is in the direction of incident ray, positive value. Converging lens means all the light rays after passing to the lens diverge, spread out, and appear to diverge from the point on the principal axis. This point is known as focal point of this lens. And the distance between this point and this point is called as focal length. It is called as divergence. Appear to diverge from the point. And this focal point lies towards the left of the lens. It takes negative value. By measuring the distance from this point to this point, optical center to this point, it is in the direction opposite to the incident ray, therefore it is negative value. F can be sign convention, negative or positive value, the sign convention. It is known as divergence and convergence. Let us come to the point, the definition of power of lens. Let us go deep into the concept. This lens I have taken converging lens, and this is the principal axis passing through the optical center. The incident ray parallel to the principal axis, just passing through it undergo refraction like this. Change the direction. It is an angle of deviation or angle of refraction. Converge to a point. This angle of deviation or angle of refraction, the magnitude of angle will represent the power of lens. Greater deviation, greater power. And this theta, when you see the diagram like this, these two are parallelized and this theta is same as this theta, opposite angles. And there is some geometry in this. Geometry is here, straight line, and this is a straight line. This is called as focal point, that is focal length. And this, let us call this as a vertical height, that is distance from the optical center to where the parallel light falls here, this vertical distance. And the power of lens depends on the magnitude of the angle, and this angle we represent in terms of tangent of angle. The power of lens, here the tangent of this angle The power of lens is the tangent of this angle. It is called as power. We can define this tan theta because this theta is same. It is in the right angle triangle. Write tan theta definition. Tan theta is equal to opposite by adjacent. Opposite side is h, adjacent is f. Tan theta equals h by f equation. And for definition, it further requires further simplification. Put h equals 1. There is a distance between the optical center and the incident ray is falling here. That is h unit distance of separation. Then finally equation takes t is equal to 1 by f. So 1 by f is tan theta equals 1 by f or p equals 1 by f. Using this equation and looking at this geometry, we can now easily define what is the power of lens. The power of lens is tangent of the angle. What is the angle? Is the angle of convergence or divergence. Convergence for this and divergence for the concave lens. Here convergence or divergence, angle of tangent by which the lens converge or diverge the ray of light parallel to the principal axis falling at a distance of unit length, unit distance from the optical center, falling at a unit distance from the optical center, h equals 1. There is a definition for power of lens. The mathematical definition is what is that p equals 1 by f. It is a definitions in wordings. So 1 by f is the inverse of focal length. Focal length inversely related to the focal length. Higher the value, lower the higher the value, lower the value, and vice versa. That is, power of lens depends on the ability of the lens to converge or what is that deviate or refract, the degree of refraction. It is called the power of lens. More convergence, lesser value. What is that? Higher convergence, higher value. That is power of lens. So there is the inverse of this f is called as power of lens. And look at the unit of SI unit of the power in SI. Unit of SI in power. Equation is 1 by f. F in meter. Then P equals 1 by m. M to the 4 of minus 1. It is per meter. The unit of power is per meter. The special name is given as diopter D. Per meter is called as diopter. Both are same. The power of lens unit is per meter or diopter. What is one diopter? One diopter is, and the focal length is 1. One diopter means 1 by 1 equals 1. What is one diopter power means? It is the power of lens having the focal length of 1 meter, exactly 1 meter. The lens having the focal length of exactly 1 meter, it is called as 1 diameter equals 1 diopter. Accordingly, you can define this. That is a SI unit. And the focal length will take the sign convention. In the same way, the power of lens will also take a sign convention, positive or negative. If the power of lens is positive, it is converging lens, converge like this. If the power of lens is negative, It is a diverging lens like this. Diverging lens. Sign convention signifies whether the lens is converging lens or diverging lens. Positive for the convergence, negative for the divergence. This is the calculations are given, simple calculation for the calculation of B using F value. Here positive, negative values. Here F equals plus 10 centimeter, F equals minus 10 centimeter. Converting to meter. 10 to the power minus 2, 10 to the power minus 1. It becomes 10 to the power minus 1 meter. Calculate P. Here 1 by F, F is minus value. Here plus here 1 by F is positive value. 1 by F, here 1 by F. So it becomes, this is 10. This becomes 10. D for diopter. Plus 10 diopter. Here F takes minus 1 by F. P equals 10. Minus value minus 10 D. Plus 10 diopter. Plus diopter indicates the lens. It is a converging lens. It indicates diverging lens by a power of 10 by a power of 10. This is for the single lenses. What could be the cases for the lenses which are in numbers or 2 or 3 or many? That is combination of lenses. Always use thin lenses in contact. The lenses like this in contact. It may be a combination of 2 convex lenses, combination of 2 concave lenses, combination of 1 convex lens and other concave lens like this. What would be the power of the combination or focal length of the combination? Here I have taken the lens 1, lens 2 convex lenses, and since it is a converging lens, look at that, the object is here. After the refraction, we get the image like this. Convergence image here. Here, convergence, that is the diffraction by this lens, first lens, we get the image here. The object is here. And the second lens here, because already the second lens here, after the refraction, it is undergo further refraction. Since it is again converging, further convergence, further deviation, we get the image here instead of getting image over here. Net image here for this object. 2 refractions. So for this lens, here is that this is equation for every lens like this. Focal length, image distance, object distance. Let us apply this equation for this lens and the same thing to the second lens. Here f1 is the focal length, f2 is the focal length for the lenses like this. For the lens 1, 1 by f1, that is the focal length of this lens, equals 1 over the, so 1 by the image distance. What is image distance for this lens is, image here, image distance is here. Minus of object distance. Here object for this lens is this object distance. Same equation to this lens. The refraction, here further refraction gives image like this. What would be the object for the lens? Object for the lens is not this object, this is object. This image acts as an object for this refraction. It is a virtual object. And this distance is the object distance for this lens, and this distance is the image distance for this lens V. And equation for the second lens, 1 over f2, 1 by the image distance is V, minus of object distance is V dash here. these two equations, for the combined effect, you have to add up the equations. So equation 1, equation 2, 1 plus 2, we get this. Left hand side, right hand side, right side. Sum of the left hand side separately, right hand side. This is addition of left hand side and addition of right hand side. These terms are same with opposite sign, plus minus get cancelled, remaining is this. This is what you get for individual lenses. Assume that as a one together is one object, there is one lens, that is effective combination. Here for combined effect, what is the image? This net overall image is this, overall object is this. For the combined effect, right hand sides are same, left hand side must be same. That is left hand side equals left hand side. This is the equation what we get. Equation for the focal length of the combination, individual focal length and combined focal, effective focal length, here FE. This is the equation, what's good. If you write them in terms of power, as you know, inverse of this is power. This power is PE. That is power for the effect. Power for the effective combination. Here power for the individual lengths. P equals this. These equations, what is that? Power equation, these are focal length equation for the combined lenses like this. These two concepts. So let us work out problems for this combination. This is for two lenses. If the lenses increase 3, 4 like this, let us say by n number of lenses, we can repeat the same equation. For 2, this is 1. For 3, 4 like this. 1 by f remains same. And equation for 3, for n number of lenses. So these are the simple problems just to work out for the power and f values for effect for the combination. There are two lenses of power, this and this. Ask us to calculate what is the effective power and what is the effective focal length. So recall this. For this equation, just P is equal to this plus this. Adding the values, we get 30 D. Plus 30 D means the power plus 30 diopter. So it's a plus means converging lens. Both of them converging lens, again further converging. More power increase, converging lens. And what is the focal length? You know this value, take the inverse of this because they are inverse related. 1 by 30 in meter we get. In centimeter it is 33.33 centimeter. And here the problem is given the value of focal length. That is focal length of two different lenses f1, m2. If they combine, what is the combined focal length? What is the combined power? Solution, recall the same equation. For the two lenses, 1 by f is equal to, substitute what is f1, f2, simplify, take LCM minus 1 by 20. So 1 by f is equal to minus 1 by 20. What is fe? Minus 20 centimeter, because they are in centimeter get. To calculate power, convert into meter. Centimeter into meter. 20 centimeter, 0.2. Minus carry. And P equals inverse of this. Minus 1 by 2 is minus 5D. After the combination, the lens behave like a diverging lens, minus. Together they behave like a diverging lens, minus. That is what the problem and the concept. And we have to understand what is the importance or application of this, that is combination and derivation like this. Important applications we have. This we can apply for a correction of the eye defect. Eye, as we know, the structure of eye, in front we have a lens, that is the eye lens, and at the back we have retina, that is spherical shape we have. At the back you have retina, in front you have eye lens. Eye lens, that is most important. This eye lens is unique, of course transparent. It is made of the specialized biological cells. Then primarily that is adapted to focus light onto the retina. So let us assume that is a lens of our eye. The lens of our eye is a convex lens, biconvex. You have spherical shape. Eye lens, it is made of special biological cells made for this. And this lens always, whatever the light coming from the object, always converge at this point, whether from a distance or nearby. Converge at this point, the focal point. You get the image. This focal point is always on the retina surface. Then only we can, what is that? Sense. Retina gives signal to brain. We sense only when the light falls here. The presence of object here. But the problem here, if the lens undergoes any kind of defect, it may be due to some kind of disorder. Due to disorder, what happens? Instead of the focal point on the retina, it may fall in front of it, displacement due to defect, or it may fall or behind this retina. Assume that the retina is there, behind the retina or front of retina. Then you cannot visualize the object here. It is eye defect. So if the focal point is what is that falls in front of it is called what is that myopia, near sightedness. And if the focal length falls behind this retina, it is called as hyperopia, far sightedness. The defect, it is mainly defect. What is the defect in the eye lens undergoes some disorder, kind of disorder. If that is the case, it requires correction. That is, correction is you cannot correct this, that is defect. You can correct using the lens. Assume that this is a eye lens, you have to use one more lens in front of it, the contact lens or glass. To correct, what is that? The focal point, that is either here or here, exactly in the retina. How do you do the correction? It depends on this. Here, if it is false here, it is more converging. We require what kind of? The lens like this to change the position from here to here. Or if the focal length falls here, it requires more converging. That is, decrease the convergence from here to here. It requires convex lens like this. So anyway, whatever may be convex or convex, you always use this equation. There is a power. So to calculate what is the effective focal length, the effective focal length is always a distance between the lens and the retina. It is corrected. So for this length, again what is that? You apply this equation. Already we have the power of lens, that is the power of eye lens. And what power of lens we need to calculate? Whether positive or negative. Using this equation, we can, what is that? To get this value, that is this value, you have to calculate what is the possible value of this, whether positive or negative, and magnitude values. Accordingly, we fix the lens like this to correct the vision. Then finds application in lenses like this. So this concept using to find a suitable lens to correct the eye defect, whether it may be a myopia or hyperopia. So this is what the concept we need to understand. It is the power of lens and its application. With this, you have completed the portion of it.